Hello and welcome to the Week 8 Math 2414 review. In this week we'll be going over mostly some parametric equations and getting into some arc length and surface of revolution area when we do this. So let's get right into it with what exactly a parametric equation is. So we're used to seeing functions where y is a function of x. But this has some limitations. And most notably, these limitations are it has to pass the vertical line test. So we could say this curve is a function of x, but a curve like this is not. So this is not a function y equals to f of x because we fail a vertical line test. Here we have 2 points, and this is therefore not a function of x. But what if we wanted to come up with an equation of this? What if we even wanted to come up with an equation of more strange lines like this? Is there a way we can do this? Well, yes. This is called parametric equations. And parametric equations are really useful because they let us graph so many more things than regular Cartesian coordinates do. And the way parametric equations work are rather than having y as a function of x, we have y as a function of t. And then we also have x as a separate function of t. So t is often represented by time, or it often represents time, but that's not always the case. Basically what we have is we have two separate functions, one for y and one for x. So let's just do a quick example. Let's say we have x be equal to cosine of t and y be equal to the sine of t. Well, if we wanted to graph this, we can kind of do it by making a nice table. So I'm going to have, for a variety of t values, I'm going to figure out what my x value is and what my y value is. So when t is equal to 0, my x value is the cosine of 0, or 1. My y value is the sine of 0, or 0. And I can go ahead and plot that on my graph, the point 1, 0. Now, supposing that t was equal to pi over 4. Well, then the cosine of pi over 4 is root 2 over 2. And the sine of pi over 4 is root 2 over 2. Well, that point would also go on my graph. Now, at pi over 2, I have x is the cosine of pi over 2 is 0, sine of pi over 2 is 1. I'm just going to start going through this a little faster. When t is pi, I have negative 1 and 0. 3 pi over 2, I have 0 and negative 1. And at 2 pi, I'm back to where I started at 1, 0. Now we'll go ahead and plot all these points. And if we follow the arc in the direction that they give us, we see that we end up with a nice circle. Or it would be nice if I could draw circles with it. Now, this is our graph represented by the parametric equations x equals cosine t and y is equal to sine t. Now, importantly, parametric equations have a direction. So parametric curves have a direction. You'll notice that as t increases, I follow my curve around this direction. So we say that my parametric curve has direction, and in this case, it's a counterclockwise direction. So you'll want to indicate when you graph parametric equations which direction they are going. And you usually do that just using some little arrows. So parametric curves have direction, that's important to remember. We can also turn this back into a Cartesian equation. So because I know that x is equal to the cosine of t and y is equal to the sine of t, I can say that t is equal to the inverse cosine of x. Now using this, I can make my handy dandy triangle. Now cosine is adjacent over hypotenuse, which means that y, which is the sine of t, is the sine of the arc cosine of x would then be equal to the sine of this triangle. So opposite over hypotenuse rather than adjacent over hypotenuse, which is cosine. I have the square root of 1 minus x squared over 1, which is the square root of 1 minus x squared. Now, one thing to note is that this is not a complete representation of my graph. Here I have a full circle, but here I have my function y as a function of x, which means it should pass the straight line, the vertical line test, pardon. And one other thing to note is because we took this square root, we might be missing some negative portions. And indeed, this is the case. When we graph this out, we actually end up with just the top half of our circle. Another thing to note is we, again, don't have a direction. If we wanted to come up with a slightly more precise version of our Cartesian coordinate, we could do that, because we know that cosine squared t plus sine squared t is equal to 1. If we take x squared, which is our cosine squared t, and our y squared, and we add those together, those should also be equal to 1. Because cosine squared t is x squared and sine squared t is y squared, which means we have this equation x squared plus y squared is equal to 1, and that gives us our nice complete circle that we remember. But again, we still don't have a direction. All right. So that's just kind of how we can go about looking at some parametric equations. We can graph it by making a table. We can graph it by converting to Cartesian and seeing if we recognize it. We can graph just by kind of plugging in points, or if you recognize the curve, you can of course just go ahead and graph it. Table method usually works pretty well though. So let's go ahead and do some practice. Go ahead and so I want you to sketch the parametric curve by making a table. Also, be sure to indicate direction. Finally, eliminate the parameter t to find a Cartesian or rectangular form equation for the function or for the curve. All right, first up, we'll go ahead and do that one. And second, we'll do that. And I'll give you a good chunk of time to work through that. All right, let's go over this. So for the first one, excuse me. For the first one, we need to sketch the parametric curve by creating a table. So we'll start by making our table. We've got our t. We also have x values and we have y values. I'm going to start at -2 and probably go up to 2 just by ones. All right. When t is -2, x is -2 squared is 4 minus 2 is 2. And y would get me -9. Nope, sorry. Yes, -9. Oh, shoot. Yep, -9. Now, when t is -1, then I have -1 squared minus 2 gives me -1. And I have -7. I'm sorry, not -7. That would be -1 times 4 is -4 minus 1 is -5. 0, I'm at -1. I'm just going to finish off the y column, then 3, and then 7. Then for x column, I'm at -2. Then I'm at -1, and then 2 again. Okay, which means I can now go ahead and graph this. So when x is when t is -2, I have an x value of +2 and a y value of -9. When t is -1, I have an x value of -1 and a y value of -5, which would put me about right there. When t is 0, I have an x value of -2 and a y value of -1, so about right there. Then I go up to 3, and then 7. Now graphing this, I end up with a curve kind of like this. And importantly, I am moving in this direction because my t values start out very small or negative, and then as they become positive, I move in this direction. So I'm going to indicate my direction on the graph. Next, I need to eliminate my variable t in order to find a Cartesian equation. So because y is equal to 4t minus 1, add that y plus 1 is equal to 4t. So t is equal to y plus 1 over 4. Which means that because x is equal to t squared minus 2, x is then equal to y plus 1 over 4 minus 2. So x is equal to y plus 1 squared over 16 minus 2. So x is then equal to y squared over 16 plus y over 8 plus 1/16 minus 2 would give me minus 31 over 16. And this is the equation of a hyperbola. Note that we can't put this in a y equals format because, again, it does not pass the vertical line test. But it is in x equals form, so we have a sideways parabola, a hyperbola. All right, for the second one, we're again going to be making a table. Now I'm again just going to go from -2 up into +2 just by 1. Now I have -2 squared is 4, 1, 0, 1, 4, and then -8, -1, 0, 1, 8. Okay. And now I need to go ahead and graph this. Okay. So when t is -2, I have x at +4 and y down at -8. Then when t is equal to 1, I have x at 1 and y at -1. And then at 0, I'm at the origin. Then at 1, I'm at 1, 1. And then at t equals 2, I'm at 4, 8. And if I graph this out, I end up with something kind of like this, which it should technically have a little more curve to it. So I'm actually going to put this point a little higher up just so we can maybe a bit more clearly see the curve. But again, my t value, when t is negative, I start out down here, and as t becomes positive, I go and trace up this way. So my direction is in that direction. All right. Now we need to eliminate and find a Cartesian form. So y is equal to t cubed, and x is equal to t squared. Now, I don't want to take the square root of my t because my square root, or if I took the square root of t squared, then I'd need to do plus or minus. I don't necessarily want to do that, but I know that t cubed is a one-to-one function everywhere. It's what we call bijective. And what that means is it has an inverse, so I can take the cube root, and then I don't need to worry about plus or minus. So I'm going to say that t is equal to the cube root of y, which means then that x is equal to the cube root of y squared, which is equal to y to the 2/3. And this would be my Cartesian form. And again, I'd just like to reiterate that the reason I went ahead and took the cube root of y to find t is because that way I can avoid having plus or minuses. So that would be my solution, where I found my table, I sketched my graph, and I found a Cartesian representation. So we haven't actually done any calculus with these parametric curves yet. So let's start talking about what happens when we want to do some calculus. First off, well, we kind of want to know what the derivative is. If we're looking for the derivative of y with respect to x, well, we're given an x of t equation and a y of t equation. So we're going to take the derivative of y with respect to t, and then the derivative of x with respect to t, and simply divide them, and that gets us dx over dt. Now, one thing to note is our x derivative cannot be equal to 0 in order for this to happen. And also, if we want to find our second derivative, we can actually take the derivative of our first derivative, but then we also need to divide by our x derivative. So this should say dx over dt. So these are kind of definitions. There are proofs in your textbook of where these come from. If you want to look those up, you can, but I don't think we have time to cover them now. So apologies if you were looking forward to that. All right, so let's go ahead and do a quick example. Let's say we have this. Well, we can find dy over dt by taking the derivative of our y equation. That gives us 12t squared. We can also find dx over dt by taking the derivative of our x equation. That's e to the t minus e. Which means that dy over dx is equal to dy dt over dx dt is equal to 12t squared over e to the t minus e. Cool. All right. Now there is a point at which dy dx does not exist, and that is where dx dt is equal to 0. That would occur when e to the t minus e is equal to 0, which occurs at t equals 1. So our derivative does not exist when t is equal to 1. Now, let's talk really briefly about horizontal tangents and vertical tangents. In Cartesian equations, so when we have a normal y is equal to a function of x equation, our tangent line is horizontal when we have no slope. And when we have no slope, we know that our derivative is equal to 0. So when we have a parametric equation, we say that we have a horizontal tangent where firstly our derivative exists, so dx dt is not equal to 0, and our derivative is equal to 0. So our numerator would have to equal 0, or dy dt would equal 0. In this case, we have a y derivative of 12t squared. So we have a horizontal tangent when t is equal to 0, because that would make 12t squared is equal to 0. Now, similarly, we have a vertical tangent. Sorry, again, just iterating that dx over dt cannot be 0 at a horizontal tangent. But we do have a vertical tangent when dx dt is equal to 0. And dy dt is not equal to 0. So in this case, we have dx dt is equal to 0 at t is equal to 1, because that would get us e to the 1 minus e is equal to 0. So we have a vertical tangent at t is equal to 1. If both dx dt and dy dt are 0 simultaneously, we don't have a horizontal tangent or a vertical tangent, and our derivative does not exist. So we can't really create a tangent line. For those of you wondering, that actually looks like a sharp turn in our graph most frequently. So if I have a sharp turn like this, then I can kind of like draw something that would look like a tangent line like that, but then also kind of like that, where it only touches my graph at the one point. I'm really bad at this, sorry. Where it only touches my graph at this one point, but again, I should have a single unique value for my derivative, so a single unique tangent line. And here, because I can draw several, I can't really say anything about the tangent line. So we say we don't have a horizontal tangent or a vertical tangent if both our derivatives are 0 simultaneously. All right, let's go ahead and find the second derivative of this same example problem. By definition, I know that this is going to be the derivative of my first derivative divided by my x derivative again. So my first derivative is 12t squared over e to the t minus e. So taking the derivative of that, I'm going to need to use the quotient rule. So that's going to be low times the derivative at the top minus high times the derivative of the bottom over the bottom squared. And again, I need to divide all of it by my x derivative, which is e to the t minus e. Now, combining this, I get e to the t minus e times 24t minus 12t squared e to the t, all over e to the t minus e cubed. Now, it's possible that we could simplify this a little more, but I don't think we can, so we're just going to leave this as our final answer for our second derivative. Perfect. All right. Time for some practice. Go ahead and find dy dx, second derivative, and horizontal and vertical tangents. For the equation, y is equal to t squared plus 4t minus 2, and x is equal to 1/3 t cubed minus 4t. All right, I'll give you a few minutes to work through that. All right, let's go over this. So in order to find dy dx, I'm going to need to find dy dt, which is 2t plus 4, and also dx dt, which is t squared minus 4. Now I can go ahead and actually use this to find my horizontal and vertical tangents, because I can tell that dy dt is going to be equal to 0 when t is equal to -2. And also dx dt is going to be equal to 0 when t is equal to -2 and also +2. Now I have my horizontal tangents when dy dt is equal to 0, and dx dt is also not equal to 0. So because I have what dy dt is equal to 0 when t is -2, but dx dt is also equal to 0 there, I have no horizontal tangents. Now my vertical tangents occur where dx dt is equal to 0 and dy dt is not equal to 0. Dx dt is equal to 0 when t is -2 and t is +2, but since dy dt is equal to 0 when t is -2, my only vertical tangent occurs when t is equal to 2. Now, I can actually find the point at which that occurs by plugging in my t is equal to 2 value into my equation, which would get me an x-coordinate of 8/3 minus 8, or -16/3, and 4 plus 8 is 12 minus 2 is 10. And that just came from plugging my value of t is equal to 2 into my x value equation and into my y value equation. Now this is also enough to go ahead and give me my dy dx, which is dy dt over dx dt, which is equal to 2. I'm going to go ahead and factor my dy dt. 2 times t plus 2 over, I'm also going to factor dx dt. T squared minus 4 is t plus 2 times t minus 2, which I can go ahead and cancel, and that gives me 2 over t minus 2. Now I need to find d squared y over dx squared, which is going to be the derivative of my first derivative. So this is going to be -2 over t minus 2 squared. I can go ahead and do the quotient rule, or I can rewrite my derivative as 2 times t minus 2 to the negative first, and then apply the chain rule. Give me -2 times t minus 2 to the -2 times the derivative of the inside, which is 1, and then thus -2 over t minus 2 squared. And of course, I need to divide by my x derivative once more, so t squared minus 4 again. Now cleaning this up a bit, I have -2 over t minus 2 cubed times t plus 2. And for those of you wondering how I got to here, again, I can rewrite my t squared minus 4 as t minus 2 times t plus 2. So then I have t minus 2 squared times another t minus 2 gets me my t minus 2 cubed. And then I also have my t plus 2 left over as well. So those are our first and second derivatives respectively. All right. So we can also use parametric form to find arc length. So our arc length formula in parametric is going to be the length is the integral from a to b, where these are our starting t values and our ending t values respectively, of the square root of our x derivative squared plus our y derivative squared. Again, the proof is in your textbook if you want to look it up, but we don't have time to go over it. So let's do a quick example. This is the same example that we had from earlier at the very beginning, where we know this is the graph of a circle. And if t is running between 0 and 2 pi, we know that this should trace out the circle exactly once, which means we should kind of already be able to tell the arc length because it's just the circumference of a circle. But we can go ahead and use our arc length formula just to double check that our arc length formula actually is applicable. So Our arc length formula tells us we need to go from our starting t value of 0 to our ending t value of 2 pi, and then take the square root of dx dt squared. Here we have dx dt is equal to the derivative of cosine t is negative sine of t. So negative sine t squared is sine squared t. We also have dy dt, which is equal to the derivative of sine t, which is cosine t. So dy dt squared is cosine squared t. Okay, now sine squared t plus cosine squared t is, of course, 1. The square root of 1 is 1, so we have the integral from 0 to 2 pi of just dt, which is, of course, t evaluated at 0 and 2 pi, which is 2 pi. And that would be our arc length. Now, the question is, does this match our understanding of what it should be? Well, we started out with a circle of radius 1, and we traversed it once, so we have the circumference of a circle of radius 1 is 2 pi times the radius, which is 1, which is 2 pi. So this does match our geometric understanding of what should be going on. Now, we'll go ahead and do a quick practice problem. If we have y is equal to 4 e to the t over 2, and then x is equal to e to the t minus t, and t goes from 0 to 2. I'll give you a couple of minutes to work through that, so good luck. All right, let's go ahead and go over this problem. So in order to find our arc length, we're going to need our dx dt and our dy dt. So dx dt would be equal to e to the t minus 1, and dy dt is going to be equal to 4 times 1/2 is 2, e to the t over 2. Which means we can set up our arc length equation. We have the integral from 0 to 2 of the square root of dx dt squared, so e to the t minus 1 squared, plus 2e to the t over 2 squared as well. Now, if we go ahead and distribute our, and FOIL out our e to the t minus 1 squared, we get e to the 2t minus 2e to the t plus 1, and then we have plus 4e to the t. We're left with square root e to the 2t plus 2e to the t plus 1 by combining our negative 2e to the t and our plus 4e to the t. Now, because we flipped just the middle term on this, and this was an a minus b squared form, we can immediately factor this into an a plus b squared form. So the principle behind this is we started out, this part we can factor exactly into an a minus b form. And when we flip the sign, it should go exactly into an a plus b form. So all we did is we flipped the sign on this middle term. Okay. Now this will cancel out the square root, so we're left with the integral from 0 to 2 of e to the t plus 1 dt, which is equal to e to the t plus t, evaluated at 0 and 2, which is e squared plus 2 minus e to the 0th is 1 plus 0, which is e squared plus 1. And that would be our arc length. All right. Now, the last topic we have to cover today is surface area. And our surface area formula is, again, going to be based on, it's basically the same formula. We have arc length times some kind of radius. So if we're rotating about the x-axis, we have a surface area of 2 pi times y times the square root of dx dt squared plus dy dt squared. And this is for about the x-axis. And of course, our y equation would be replaced by some parametric form of y, so y is equal to some function of t. And if we're going about the y-axis, well, it's the same thing. Just instead of having a y, we have an x. And again, our dx dt squared plus dy dt squared is our arc length. So, and this would be for about the y-axis. Okay. So if we did a quick example, we're going to find the surface area of a sphere. And we can find the surface area of a sphere by rotating a half circle about the x-axis. So y is equal to sine t, x is equal to cosine t. But because we're only rotating a half circle, we need t to go between 0 and pi. If we rotated a full circle, we would actually end up double counting, because rotating a half circle throughout the entire sphere is sufficient to give us, well, it's like you can think of it, if we have a half circle and we spin it around all the way, well then that would get us a complete sphere. If we rotated a full circle around, we would only need to go rotate it halfway around to get a full sphere. So we're just going to use a half circle to find our whole sphere. So we know that our surface area is going to be the integral from 0 to 2 pi, or sorry, from 0 to pi of 2 pi times our y value. We're rotating it about the x-axis here. I should just draw a little picture real quick. There's our half circle, rotating it about the x-axis, and that will get us our complete sphere. Something like that, roughly. So we have 2 pi times our y value, sine of t, times the square root of x of t, or dx dt squared plus dy dt squared. Remember, dx dt is negative sine of t, dy dt is equal to cosine of t. So dx dt squared is sine squared t plus cosine squared t, and then dt. And because all of this goes to 1, we can essentially ignore it. So we have the integral from 0 to pi, or 2 pi sine of t, which is equal to negative 2 pi cosine of t, evaluated at 0 and pi, which is of course equal to negative 2 pi times negative 1 minus negative 2 pi times positive 1. And this gets us negative gets us 2 pi, plus 2 pi is 4 pi for our surface area. And this actually matches with our geometric knowledge of surface areas of a sphere. Surface area of a sphere is 4 pi r squared, and in this case, because our radius is 1, we have 4 pi times 1, which is 4 pi. So we do indeed have the correct surface area. Now we'll really quickly do a practice problem. Find the surface area. Given y is equal to 8 root t, and x is equal to 2t squared plus 1 over t. And t ranging between 1 and 3. And I'll give you a few minutes to work through that. Good luck. All right, let's go over this problem. So to find our surface area, well, I suppose I should have told you where you're rotating about. I hope you just assumed the x-axis. That's on me. So about the x-axis, so that means that our general form is going to be the integral from our starting to ending point of 2 pi times our y times the square root of our dx dt squared. Dx dt in this case is equal to 4t minus 1 over t squared plus dy dt squared. And dy dt, that's 8t to the 1/2, so we have 1/2 times 8 is 4 over t squared. From here, we can just do some super fun algebra. And that gets us 16 pi times the square root of t times the square root of, if we FOIL out our 4t minus 1 over t squared, then we get 16t squared. We have minus 8 plus 1 over t to the 4th plus 16 over t to the 4th. I feel like I'm doing this wrong. Give me 1 second. I am doing this wrong. This should be, I messed up my derivative. That should be a t to the 1/2. Okay, which would give us just 16 over t. And also, this should be 8 over t as well. Okay, there we go, much better. I was trying to skip a few too many steps. So we have 16 pi times the square root of t times the square root of 16t squared plus 8 over t plus 1 over t to the 4th dt. And again, we can use the same factoring technique we did in the last one to factor this into a 4t plus 1 over t squared, which then means that our surface area is equal to the integral from 1 to 3 of 16 pi times the square root of t times 4t plus 1 over t squared. Now I can go ahead and pull my 16 pi out of my integral and also combine my root t with my 4t and with my 1 over t squared. So this would become 4t to the 3/2 plus t to the minus 3/2. Now when I go ahead and evaluate this integral, I have 2/5 times 4 is 8 over 5, t to the 5 over 2, minus 2t to the minus 1/2, evaluated at 1 and 3. And I can go ahead and plug in these values. I get 16 pi times 8/5 times 3 to the 5/2 minus 2 over the square root of 3 minus, and then I have 8/5 minus 2. And I can go ahead and compute 8/5 minus 2. 8/5 minus 2 gets me negative 2/5. And then negative negative makes it positive, so I have a surface area that's not a very pretty number, to be sure, but I can do 16 pi. I'm going to go ahead and factor out 1 over the square root of 3. Actually, I'm not. 16 pi times 8/5 3 to the 5/2 plus 2/5 minus 2 over the square root of 3. Or minus, sorry, Yes, minus 2 over the square root of 3. And that would be my final answer. Alrighty. Well, that is all that I have for you today. So thank you very much for watching, and have a nice week.